Hello, and welcome to Homework 5, Part 3, where we'll be deriving the expression for heat transfer rate, Q, in terms of the overall heat transfer coefficient, U, area available for heat exchange, A, and the log mean temperature difference for a co-current heat exchanger. Explain why this is also valid for a counter-current heat exchanger. All right, so for our co-current heat exchanger, it will also be a parallel flow heat exchanger, and with it, um, a lot of assumptions. Uh, Kinetic energy and potential energy changes are negligible. Um, the only heat transfer that's happening is between the fluids inside the parallel flow heat exchanger, and um, the fluids, whether it's the hot stream or the cold stream, have constant heat capacities as well. And so, what does it look like? Well, like I said, we have a parallel flow heat exchanger. So we have some hot fluid coming in, some cold fluid coming in, and between the two, there's some heat exchange happening, and there's some differential area where it's able to perform that heat exchange. And then the new temperature is some uh, differential change that is added on to then the original stream. So kind of looks like this, right? And I said something along the lines of a specific heat capacity, and we'll get to that a bit later. But for the figure, at least, there's something called these heat capacity rates that are specific to the fluid in each case. And so if we were to model the temperatures, it looks something like this for a co-current. So you have some cold and some hot fluid going in. At, let's say the inlet is position 1, there's some difference in temperature at 1, and then after some change at position 2, that's the difference in temperature at position 2. We can say that there's some temperature difference at wherever position we want. And let's say this is the heat flow. Well, then this is dTH, and this is dTC. And so that's what our figures look like. And on the phone cam, that should be viewable. And so let's move on to the equations, right? I said something about these heat capacity rates, and it actually deals with something along the lines of the specific heat capacity of each fluid. And so we can model the differential heat flow, dq, as the mass flow rate of the hot fluid times the specific heat of the hot fluid times whatever differential change of the hot fluid. And we can combine then these two terms to get our our heat capacity rate, which is that CH. And we realize that heat flow goes from the higher to lower temperature, right? And so this stream, you could say, is losing heat. We can then represent that for the cold stream as well. And so the mass flow rate in the cold stream times the specific heat of the cold stream times the temperature change gives us that heat flow. And then combining the mass flow rate and the specific heat capacity, we get our heat capacity rate for that fluid. So we get these two equations for our differential heat flow. And so just as a little setup, we can sort of integrate these for our overall scenario, right? So across, let's say, from position 1 to position 2, We integrate it, so we get uh, some heat flow, right? Heat transfer times negative CH. This is constant, like I said earlier. And now this is the difference between the outlet minus the inlet, right? Or 2 minus 1. Let me do that for the cold stream as well. And I'll simplify this now, as in distribute the negative. So we get CH, TH in minus TH out. All right, and so that's just some setup that I'll do ahead of time. And so we can actually represent the heat transfer rate uh, Q, or in this case, the differential heat transfer, right? In terms of thermal resistivity concepts. And in that case, we have dq being equal to, well, the resistance, right? In this case, all the thermal resistances will be captured in our overall heat transfer coefficient, which is U, which is the inverse of our thermal resistivity, times the temperature difference, which is our driving force, right? So dq is our current if we're applying that concept. And then it's going to be multiplied by the differential area that is available for heat exchange. So we'll let that sit for now. So we have this delta T. Well, if we were, this delta T is the temperature difference between the hot and cold stream, not the temperature difference between, let's say, up here, where we have the outlet minus the inlet. And so if we take the derivative of that, well, if we express this temperature difference as a derivative, well, we would see that it would be equal to the derivative of the hot stream minus the derivative of the cold stream, right? That's the delta, the difference right here. And well, if we look up here, we have an equation or expression that we can sort of solve for delta TH here, differential TH here, and differential TC, which we can plug it in. So let's do that. This is simply moving the negative CH over. So we get dq over CH minus dq over cc. Pull out the dq, negative dq, times 1 over ch minus 1 over cc. And we have this expression for dq that we can then plug in for here. And you can see we have terms where we can move around to then set it up as an integral, which is what we'll do next. So we'll get the t delta t integral negative u. Our heat capacity rates are constant. And so we perform this integral, and we get the natural log of the temperature difference at 2 over the temperature difference at 1 is equal to negative u times the total area times 1 over ch minus 1 over cc. And so our then integrated terms here, we can then solve for 1 over the inverse of the heat capacity rate for the hot stream and then the cold stream, and plug those in so we can have our heat transfer rate term back into our equation. And so what we get here is, let me see if you guys can see this. Yeah. Delta T2 and so for 1 over CH, we'll have divide this over, divide Q over. So we get THI minus THO over Q. This should be a plus when I pulled out the negative dq. Sorry about that. Plus TCO minus TCI over Q. All right, we can pull a Q out. UA over Q. And we get THI minus THO plus TCO minus TCI. Let's sort of rearrange this for position 1 and 2, right? Because we have those terms available. Because we know that position 1 is the inlet and position 2 is the outlet. And so we get so we get minus THO plus TCO. So we can turn this into delta T1, and we can turn this into delta T2 if we factor out a negative. And so we need to factor out a negative, factor a negative. And so that turns our equation into, so you can see this, is equal to negative UAQ delta T1 minus delta T2, because that's our factored out negative. So we apply that negative to negate this, or to, I guess, rearrange the difference here. And then we can bring our Q over. So we get Q is equal to UA, our heat transfer rate, is equal to our overall heat transfer coefficient times our total area available for heat exchange, times the temperature difference at 2 minus the temperature difference at 1, or inlet and outlet, or outlet and minus inlet, over the natural log of the temperature difference at 2 over the temperature difference at 1. So this portion right here is the LMTD, or the log mean temperature difference, for a co-current heat exchanger. And, well, we can actually say it's for a counter-current heat exchanger as well, because if you look at the expression that we derived for our heat transfer rate Q, it doesn't specify direction of flow in any case. It just requires you to have the temperature difference at the at the inlet and outlet. And so this is why it would be valid for a countercurrent heat exchanger as well. Just speaking further on it, if you had a counter, let's say like this, so right, this would be your position 1, your delta T1, and this would be your delta T2. And so counter current heat exchanger will always be, just speaking more on heat exchangers in general, counter current will almost always be the best type of heat exchanger, as you can continuously exchange heat at a higher rate for a longer time, for a longer distance or area, I should say, because that difference will always be on average higher for a counter current compared to a co-current. And so, yeah, this heat transfer rate Q expression that we derived is valid for both co-current and counter-current, because it only requires the temperature differences at the whatever two positions that you are interested in. So that is the end of Homework 5 Part 3, and thank you for watching.